All right, well, how's everybody doing?
Doing good, doing good.
All right,
No,
all
nothing's
right,
on fire in Redondo Beach.
that's good. Definitely smoky here in Long Beach. I wanted to show everyone before we got started. I know I'm new to Canvas. I kind of was making the assumption that you guys knew how to do it, but I want to go over real quick, um, sharing the Canvas screen here. Okay, so when we go for the homework, um, I'm on my student view. So for the week, for any of the homework assignments, when you click on them, you'll get the assignment. So this one was just, please acknowledge you've read the syllabus by typing your name in the text box. You have to click submit assignment. I already did the test, so that's why it says resubmit. But you have to click up here, submit assignment. And then you could type in whatever you can type in. And then you click submit assignment again. So it's 2 clicks of the submit assignment. And then you get this confetti. Yay, you've submitted. And it should say submission check. So please do that for assignment number 1 at some point here, and for assignment number 2 after this class. But I just wanted to make sure that you click that assignment button twice, and then you get that submitted status kind of up there in the corner. So any questions with that? As far as the other stuff on Canvas goes, you'll have your PowerPoints, your Zoom link. Let's see. Did I put the other ones here? No, I didn't. Okay. Okay, that's pretty much all I had on that. The other one, I guess if we're on this recording, let's go to YouTube. If you go on the playlists on YouTube, you will have a radar playlist under my channel. And the link to my channel is Bree's tutorial videos on the side of the Canvas. So if you click on that, it brings you to this. Open it in a new tab, and it brings you to the channel. Now I am doing 2 different classes right now to sort out all my little videos. You could just click on the radar playlist instead of the other ones there. And right now I just have the one of last week's recorded Zoom call, so, or Zoom class, whatever you want to call it. So let me know if you guys can't access that. You should all be able to. I'm pretty new to YouTube, so I'm not exactly an expert, but yeah, let me know if you can't, and I'll try to make it so you guys can. But those were my 2 things I wanted to go over: the Canvas assignments and the class recordings. Once we start doing some more radar plotting sheet homeworks, meaning starting next week, I'll start doing homework tutorials, and I'll do all of the homework assignments on video. Hopefully we'll get most of them done in class, but I will do all of them on a separate homework tutorial video. But that's once we get to those problem assignments or the actual paper plots. So yeah, that's about it. How are you guys doing? Catching up with all your other classes? I guess we're more than halfway through the semester for you guys.
Yeah, I'm loving it. I'm old AF and back in college after like 35 years, and I'm really stoked to be in the professional mariner program. I think it's just absolutely fantastic. And all of my classmates, you guys seem to be really, really sharp. It gives me hope for the future in my old age.
Well, that's good. All right. Well, today we're going to go over some more of that that fun radar theory that no one likes to talk about. So we'll go a little bit into that, and then we're going to dive into just an intro and familiarization with the radar plotting sheet. So if you have these, was anyone not able to get these? Okay, that's good. If you have those, we're going to be using them towards the end of class. Just kind of messing around, not really doing an exact problem, but I'll be showing you and getting familiar with it. So next week, we can dive into some real work on the radar transfer sheets. Okay, so that's what's going on. Let's get to share. Why can't I share? Sorry. Share my PowerPoint. Okay, we can see the PowerPoint, right? Thumbs up? Yeah?
Yes.
Okay. Cool. So this is, we're going to be talking about factors affecting our radar. So last week we kind of discussed what, how the radar essentially works. And then these are all going to be things that help us interpret what we're looking at on the radar screen. That if there's all sorts of different factors can really give us a, poor quality radar resolution or great, and really help us with our situational awareness. So we really want to be able to know what's going on around us and adjust our radar in accordance. So let's get started. So here's a list of kind of a bunch of different things that can affect it, and we're going to dive into all of these. So we have the height of ourselves and the height of the target, the amount of energy transmitted, the distance, the composition. All of these things are kind of going towards our how we get that blip on the screen is we send that electromagnetic frequency out, it hits an object, and it comes back. Now, we know it comes back at a much weaker pulse than it is when we shot it out. We shot it out very powerful, and we want it to come back, and then we magnify it to get that little blip on the screen. So we want that blip to be as best as possible. So all of these different things kind of say how much return are we going to get if it's all these different kind of things. So
Question?
yes.
The weaker strength coming back that you have to amplify. Does the given weakness of that strength tell you something about the contact characteristics of that? Is it like based on the strength of that return?
Yes, and it can be, when I go back to this, it can be all of these things. So when you get a weak return coming back, we could be distance, it could be geometry of the vessel, it could be our pulse repetition rate, it could be all of these different things. It could just be one, but we want to be aware of them. So if we can adjust something, then we can, or we can just be aware if we're getting very weak returns in this area, then we might, have an extra lookout and kind of be looking out in that area, just to give you that that broadened situational awareness of I'm seeing something, but I'm not really sure if I'm seeing something, because the radar can be very deceiving sometimes.
Okay, and has radar gotten to the point where the strength of that signal will tell you the composition of that target, like if it's hard or soft, if it's I don't know, if it's a boat or a whale?
Well, it won't say, hey, this is a boat or this is a whale, right? But we would have to use our knowledge of studying the radar to kind of differentiate between two different things. And then what also helps are those overlays that I talked about last week. If we overlay the chart, then we can see, oh, this is most likely a buoy, and I'm getting this weird return on it. Or this is most likely a vessel in the channel, or a vessel coming out of a harbor. Or if I have AIS, that confirms that it's a solid vessel, even if I'm getting a weak return. Hey, that's an actual vessel because I have this AIS overlay on top of it.
Gotcha. Thank you.
So all those things can help, but we just want to be aware, because some of these factors can affect our basically our minimum and our maximum distance that we can see with our radar. So even if we have it set to 24 miles, can the radar really see 24 miles? Maybe, maybe not. If it's set to 0.75 or 0.5, I don't know what the smallest is on our recreational ones. Can it really see and give us a good description of what's very, very close to us? So there's those minimum kind of range and the maximum range, and we want to get the best possible picture within those minimum and maximums around us. So that's what we're going to be talking about today. So when we're looking at a target itself, there are a few things that we talk about. We talk about the height of the target. Is it, a low kayak, or is it a tall car carrier or something? If it's very, very low, it's going to be harder to get that contact, that reflection back to our radar. Basically, the size of the contact. So this is all about the contact itself. The size of the contact, if it's, bigger, it's going to reflect more pulse back at us. The aspect, and I'm going to go into each of these so you don't have to know all of them. The aspect is basically which way the boat is pointing. Here's a little boat here. Is it pointing side on, bow, kind of bow, stern? Which aspect are you looking at? And that's also really important when you get into the rules of the road and figuring out what kind of situation, if there's risk of collision, what kind of situation are we in when you see the aspect of another vessel. The shape of another vessel, again, goes with that return. The texture, the composition, all goes with how much return you can get. So those are on the target itself. And then we're going to talk about other ones as well. But let's dive into these. Some of you guys have maybe in like a nav class might talked about visibility and the geographic visibility of a light. Have you guys calculated geographic and luminous visibility in any of your other classes? Okay. So this is basically the same kind of thing. The higher you are and the higher the target is, the more likely that you'll be able to see it and also get that reflection off of it. If you are really low and the target is high, you could probably see it. If you're really low and the target's really low, that range that you can see one another is very short. So the higher the both of you are, the bigger that range is. And that's basically because of the curvature of the Earth. Does anyone remember the formula for measuring geographic range? (1.17) times the square root of the height. Ring any bells? Not ringing any bells.
Negative.
I was gonna say something to do with pi times the radius.
No, it's easy, just 1.17 times the square root of the height. Add both of them up. Guys don't do luminous range either. Anyway, okay. That's not this class. I'm not talking about this. Okay. Moving on. This is again, the higher you are, the higher the object is, the more likely you'll be able to see it on radar. So even if your radar is set to 24, 36 miles, you might not be able to see that far with the curvature of the Earth. This is our size. So again, with a larger contact, you're going to get a stronger echo, a stronger return. With a smaller contact, it's going to be a lot weaker. I'm not saying it'll be impossible to see, but it will be a lot weaker. If you have high filters on, you know, that sea clutter or rain clutter, or it might miss it, so you'll get that echo averaging out a few times. So again, you might not see smaller targets strong on your radar screen.
Does your radar pulse change in size? I mean, I would imagine as it goes out, it may widen, but can you adjust it?
I'm gonna say no. You typically do not adjust your radar. Different frequencies, you know, we have the 10 centimeter and the 3 centimeter. The 3 centimeter is a high frequency. The 10 centimeter is a lower frequency. So those have different, their, I guess, echoes or pulses look different. And that's what gives one more qualities than the other. Our 10 is for long distance, right? Open ocean. Our 3 is for coastal, close range. So those, they will be different the more radars you have on board, but typically I'm going to say you're only going to have one radar on board and you're not adjusting with the pulse rate. Okay. Oh, we got some little animation here. That's cool. Okay. Okay, aspect. Again, this is aspect. Okay, I like this one better. So we'll get our little animation. So if we have aspect, this is you, and their bow is facing us, some of those returns can be deflected to the side or other which ways. So the one that we get directly back to us could be a very weak signal. If we get a return right on the beam, that's going to be our strongest reflection back at us. If we get one on the stern of the vessel, it has less area to give us back, but it is most likely pretty flat. So again, we're just kind of thinking of what's the best possible situation for us to get that strong pulse coming back towards us, because that's the whole concept of radar, is we're sending these pulses out and we're getting them back. So we want to maximize that that possibility of getting good returns coming back. So the aspect of a vessel can affect that. The amount of energy transmitted. So the more energy that transmits out, the more that will come back. So it gets weaker and weaker and weaker as it goes farther and farther away from you. And then when it comes back, it's even more weak. If it starts off really strong, really powerful, then it's going to come back a little bit more powerful. So that one kind of just makes sense. Distance, right? The closer the targets are, the more energy that they're going to return. The farther away they are, the farther our pulse weakens as it gets farther and farther away. And then when it comes back, it's even more weaker because it has all this time to travel. And when I say has all this time, this is like millionths of a second, right? This is like, I can't even comprehend how short this is. But technology is amazing, and that's the way it is. So yes, the closer targets, we get more energy than the further ones. Okay, when we look at more characteristics of the vessel themselves, their shapes, their textures, and their composition can all affect how much return they're coming back to us. So this little picture here is some sort of military stealth vessel, which is supposed to be undetectable by radar, because anything that comes up, it bounces some sort of other direction. So it's supposed to be undetectable by radar in a little stealth, but I don't know. I've never seen one in real life.
I think it's also got the carbon fiber composite, so it absorbs rather than reflects. Does that make sense?
Yes. So this next slide is our composition. Wooden boats, fiberglass boats are poor reflectors. The metal, water, land, ice, those are going to be good reflectors coming back towards us. So, so we want to keep that in mind. If you guys are doing any ice navigation, it's on here as a good reflector, but it is more of a fair reflector. It is very hard to see ice and bergy bits at night. We would use, what are they called? Night vision goggles to try to see different ice on the water, because it was very hard to detect. Geometry of the vessel, again, flat or concave, like curved inwards surfaces are really going to give you that reflection back. Those rounded surfaces or real straight, not perpendicular surfaces are going to give you that poor reflection. So it's all about getting that echo back to our radar antenna. The condition of the radar equipment. So this is moving away from looking at the target itself and more at looking at our equipment. So we're kind of shifting in our factors here of not looking at the target, but looking at ourselves. So a poorly tuned radar, obviously not perform well. But also we have, is it sooty? Is it salty? Is it greasy? What if there's a film or something around that radar antenna, it's going to be a lot harder for those weak echoes to come back. So yeah, we got to make sure everything is, hopefully we maintain our boat pretty well, so we're good. The frequency, I kind of went over this. That 10 centimeter S-band is for long range, is for open ocean. That 3 centimeter for coastal short range scanning. That, the 3 centimeter has a really high frequency, and the high frequencies kind of peter out, are more subject to scattering than the lower frequencies. So they don't last as long. They have a lot of energy, but they don't last as long for longer distances. So for our long range scanning, our open ocean has the lower frequency, which makes it last longer. So the power within it, because it is a lower, it's not going up and down like this, it's kind of mellow, if you will. It can go a longer distance than using all of its energy at a much higher frequency. So that can give us our maximum range. We're going to have a much bigger range on the 10 centimeter than the 3 centimeter. And when I'm saying this, maybe I have both a 10 centimeter and a 3 centimeter on 24 miles. I might get, all of a sudden, I might get a, target picked up on the 10 centimeter at 20 miles, but I won't see that one on the 3 centimeter until maybe 10 miles or something. It wouldn't pick it up until a certain distance. Now, if you see something on the radar 10 miles out, that's probably pretty good, right? I'm not saying like, if you don't see it when it's 10 miles away, collision is imminent, right? This is just like really maximizing our capabilities here, I guess. I just wanted to give that little caveat there. Okay. Our pulse length. So the pulse length, let me get this picture, has this time that we emit that pulse out, and then we have that waiting time, that listening time until it comes back, and then we send another pulse out. So the longer our listening time is, the longer the range that target or that pulse can go out, reflect on something, and come back. So if we have this real short pulse rate, our maximum distance that we're going to be able to see something is much shorter, because we're sending out another target and not another pulse, and then not listening, sending another one out and not listening as long.
Can you say that again?
Okay. Let me take a sip. So the pulse on the radar gets sent out, and then we have this waiting time. So as the pulse is traveling, right, traveling, hits something, comes back, and then we get that signal. And then at the end of that listening period, it sends another pulse out. So that the longer the listening period, the longer of a chance, I guess, that pulse has to reflect off of something and come back. So if I have a short listening time, meaning a short pulse repetition period, I think that's what it's called, or frequency. If I have a short one, then I'm limiting the time, and this travels at the speed of light. So I'm limiting that time that the pulse can go out, reflect off something, and come back. So I'm kind of shortening my maximum distance with the shorter time. Now, when I have shorter times, I'm getting more and more pulses out there with more of a chance for something to return. So I might get like a clearer, crisper picture, and it might not be just big blurbs. So there's kind of this balance of finding your way of, do I want it to be shorter? Do I want it to be longer? Let's go back to the writing stuff. I liked the picture, the writing stuff. A detected echo produces the light beam, and then it has to, the duration of the echo is the pulse length. Okay. The pulse repetition rate, PRR, determines the maximum measurable range of the radar. If an ample time allows in between pulses for returning echo are blocked by the next pulses that go.
How do you know if you are giving a sufficient amount of time between pulses or not?
I would say that you're not picking up things past 8 miles, or for some reason you can't pick up anything at a whatever, that will be different depending on how high are you, all of those other things that we talked about. But if you're never picking up things past 8 miles, or I don't know, 5 miles, I don't know what it could be, then you might want to check out see what your pulse repetition rate is and what the recommended pulse repetition rate is per your operating manual.
Is there usually like a default setting on it?
Yes. And I'm going to say usually you just go to default settings. Usually I'm going to say 99% of the time, everything's in default and you're in auto tune. That is the best way to do it, to trust the technology. Okay. Okay, now we're going to talk about beam width. So each little beam, now again, I forget what my number was last week. We get like 9 pulses per 1 degree of the 360 degrees of our circle. So this is going out a lot of times. But that beam width can actually, it starts from you, and the further it goes out, the bigger it gets. And that beam width can be very big, and it can give us this distortion of objects, which will tend to kind of give us these enlarged or bloated either targets or land masses. So we want to, and that is also why you want to be, or when we're using radar for navigation and we get a range and bearing off of an object or a piece of land or something, ranges are much more accurate than bearings when it comes to radar because of this beam width. Let me go back here. So we have horizontal beam width and vertical beam width. Now when we're talking about this, let's see. I think I have a picture that I wanted to show. Okay, this is it. Okay. It's animated, so that's fun. We have a wide beam width and a narrow beam width. Look at this. When we have the little sailboat. Oh, it only goes twice? I guess it does. Oh, it keeps moving along. Okay, so if we have a narrow beam width, we are going to be missing that sailboat because we are so tall, we are going to not see things in this area. If we have a wider beam width, we would most likely see it, but it could be distorted. So it's kind of like, again, finding that balance of what we're looking for. This one, again, goes with our contact characteristics. How much of that target is reflecting back at us? Let's see. More beam width stuff. So the smaller isolated targets, if our beam width is going to reflect back, if this is aspect of the stern, it was just going to reflect back and we'll get a little blip on the radar. Now, if we have, here we go, 2 different targets that are very close together, same range, but close together and spaced less than a horizontal beam width apart from one another, the radar will not be able to detect a difference because they're only a beam width apart. Now that beam width grows and grows the further away, the bigger the range is, right? The further away it is from us, the bigger that horizontal beam width will get. So if it's very close, you're like, how likely is it that there's going to be 2 things, 2 targets, a beam width, and when the beam width is so small? Well, that beam width grows the further and further away you are. So if you're 20 miles out, that beam width is going to be pretty big. So if you have 2 targets that are close to each other within a beam width, you're only going to see it as 1 target. And this also happens when 2 targets pass close to one another. So say these, I mean, most likely these 2 targets are going to be moving as well. So maybe they start, away from each other and then they pass each other. They don't hit each other, but they pass each other and keep going. You can get this thing where the targets swap, or the averaging of the two gets stuck in this point where they are close, and then you will get false information as they get further and further. Once they get further and further, you have to allow that radar to keep looking at it and averaging out those echoes again to get a better return. So that target swap does happen. I've seen that happen a lot. But
does the addition of AIS limit that crossover confusion at all?
That would limit the confusion for yourself as the person interpreting the radar, but the AIS is just an overlay. The AIS is not actually, helping the radar or anything. It's just an overlay of information. So it helps, you as the interpreter, the navigator. Okay. Oh, we got an animated one. Okay, so those are two targets right next to each other, and we just get one blip on the radar. Do we want to see it again? There's our little beams, and we just get this one blip on the radar. Now, if we see another one, when these targets are separate, we'll get two different blips on the radar, two different little contacts. Let's see it again. Okay. Does anyone know Captain Ron? I think Lucy did. Captain Ron made the animation on these things. It's a pretty cool little PowerPoint. I'm sure it took him a long time. All right. Okay, so we're going to kind of dive into this concept of pulse length. So let's read it. The ability of the target to show two separate and distinct echoes of two objects at the same bearing, but at different ranges. So instead of two objects being next to each other at the same range, they're going to be same bearing, different range. So one behind the other. And okay, this is the image. Maybe this clarifies things. So this is me, and I have two targets on the same bearing, but different ranges. Now, if you could remember back to last week, I said one of those cons to a radar is it can't see behind things. It can't see behind that jetty or behind that big ship to see the small ships behind it. Once it hits something, it's going to give us an echo, and it's going to be very hard to see anything behind it. So we're going to kind of look at that. So this is saying that if targets are for a pulse length of I'm going to say microsecond, but that's probably not right. 1 something of a second. The radar will not be able to distinguish between two targets that are 150 meters or less apart. So it needs time for that echo to hit one target. Some of that echo is going to keep going, right? So if we look at, an echo or hitting an object, there is more of it. If it's just one echo, some of it is going to be reflected back, but there is more energy, if you will, that is still going to go and be dissipated along the way. So if something is detected further away, it's possible to get it back, but it's definitely going to be a weaker target. It's possible, I guess, is what I'm saying. And this is what it's saying is if it's less than 150 meters apart, it doesn't have enough time in that listening period, if you will, to get that weak echo returned back to you. excuse me. What's that? So, we got some animation. If they're less than 150 meters apart, we're just gonna get one blip on the radar. If they're more than 150 meters apart, come on, we get two blips. Two blips on the radar. Do I have another one? No. Okay. Hopefully that makes more sense. Let's see, what do we got here? The effect of the pulse length and beam width distortion is related to the position of the scanner with respect to the target. So important information when measuring ranges and bearings. Be as zoomed in as possible. So for more accurate measurements, you want to be as zoomed in as possible so that you are getting a clearer picture for your bearings to come back to you, or your echoes to come back to you. So bearings should always be measured by the center of the target. So I guess we are not going to do this, but when you see one on a radar screen, you always want to measure it, and then we're going to put it on our plotting sheet. And when you measure the range and bearing using your EBL and VRM, you want to measure the middle of that little blip. So if that blip is this big or this big, or however big it is, you want to measure the middle of it for your bearing. And then you want to measure the closest side to you as the range. So the range is on your VRM as it gets away from you. When it just touches that blip, that's the range. And then the middle of the blip is going to be the bearing. So I am going to show you, let's see. Hold on a second. Uh-oh. Close this. Sorry, hold on. So maybe I play this. Okay. Okay, can everyone see this little radar screen? Is that what we're looking at? Okay. So this is a little video of the screen that we would have been looking at in class. You could see these little blips. Here's our little blips, blips, blips. So you can see this blip is kind of, elongated, if you will. It's more of a little oval. This one definitely an oval. So everything behind, it's kind of like bright yellow, and then it's kind of this lighter yellow, if you will, behind it. That's what I have on as trails. So it's giving me kind of the history that it was there, and it's just giving me the history, the trails of what the target was doing. But the big brightest one is what is kind of most current. So you'll get different shapes, if we can see that. So when you're measuring a target and transferring it to the paper plotter, you want to measure the bearing, so to the middle of the target, and then the range to the very edge. So not a lot of people like to do the middle for the middle for both and just kind of average it out, but you want to do what's closest to you, which would be what's closest to the center. Any questions on what I'm looking at here?
So you are the center of the screen. And when you're taking a range, you're going to go just to the very inside edge of that target?
Yes. So I should have left this on center. This is actual offset a little bit. It's just so I could see more targets on the screen. So this is the center, or this is me, and everything is reflecting around me. And you can see that I am actually not in the center of the circle, which makes it a little confusing, but that's the way it goes. Yes, so here we have our EBLs and VRMs. So I have my VRM set to 1 nautical mile, and that's what this circle is. It's our VRM at 1 nautical mile. So it's set there, and I can adjust it.
What does VRM stand for?
Variable range marker.
Thank you.
Do you know what EBL stands for?
Elbow?
Anybody? What does the B stand for in EBL?
Band? Bandwidth?
No. So we have a range and a bearing.
Bearing.
Right? Or range and bearing. That's how we're going to get our distances. So VRM is our variable range marker. Our EBL is our electronic bearing line. So let me close out of this and bring up another picture. Stand by. Where are my pictures?
And Captain Bree, remember that thing we talked about before class?
Yes. Okay. Okay. Real quick here. I guess I'm showing you because I can't find the picture. Back to our Canvas page. Let's see where it's set here. We have our EBLs and our VRMs down here on this radar. So our EBL, we have our heading flasher, and then this is our EBL. So it is on this target, if you will, at 063-ish. So we have 063 as an EBL, and then we have another EBL up here pointing to that Raycon, and that's at 345. And then we have our VRM, our range circles, and that is set there. So see how it's set to the very closest possible edge of that Raycon to get a distance off of it? That's where we want it to be set off of. Now, I think maybe that he was trying to get a range off of this one. I don't really know what he was trying to do here. Because you'd want it to pass the middle of the target for the EBL, and then the very edge for the range. And you want to be on the closest scale possible. This one is 12 miles.
Are the little blue lines coming? Yeah, right there. Those are they the trail?
Yes. Yes. So many different radars you can there's usually like a quick button like day or night mode. Night mode is typically red with a green. Day mode, you want brighter so you can see it. So it's typically green with that blue, but there are all sorts of different settings and colors you can make along the way. But yes, in this picture, the blue is that history, is that trails. So yeah, okay, stop share. Let's take a quick break here. Let's take a 10-minute break and come back at about 7:05. We got a thing. Cool. All right. We'll see you in a minute. Hello.
Well, we're still only trailing by 1.
All right. Not bad.
Yeah. I have hope.
I
feel bad. I feel like I'm the only person, that or I'm hogging everything.
No, it's all good.
Okay, good.
Hey,
Joseph.
I did want to clarify, Louise had a question about that PRR or pulse repetition rate, or also known as pulse repetition frequency. That can change most likely, or most modern radars, it will change on your that frequency of how much listening time is in between will change as you scale up or down. So depending on the scale of your radar, if you have it on 6 miles, if you have it on 12 miles, if you have it on 24, that will change automatically as you scale up or down. Does that make sense? Okay. Let's see. I was just looking it up. I don't know if any of you guys have seen this book before, the Radar Observer Manual. Highly recommended. It's a great, probably only a couple bucks on Amazon. It's pretty small little book if you're real interested in radar. If you're not, no needed. Okay. They have a lot of practice problems. That's where I get a lot of the practice problems from. So we'll be diving into that. How you guys doing? Any questions so far? All right. Let's share. Close. Okay. Is this where we're at? Maybe past that. Okay. We don't have too many slides left, so this is going to be another short class. Just so you guys can prepare yourselves. I feel really bad about that, but we don't have simulator time, so I really don't think any of our classes are going to go till 10:15. Hope that's okay with you guys. I am always here if you have questions, but definitely when we get into doing more of the homework assignments, we can stay on longer. But if you guys need to cut out short, I'm cool with that too. Okay, what we're looking at here. So to basically zoom in to have as small a scale possible when you're taking your range and bearing of targets or for navigation to make sure that you guys get the most accurate measurements. This is repeated. Okay, performance standards. So I kind of there's one picture a while back on the slide that showed how that beam width can affect the accuracy. It can kind of bloat or swell up targets or land features. Now there has to be some, performance standard, I guess is what we're talking about here. So the IMO, does anyone know what the IMO stands for?
Is that the International Measuring Organization?
Maritime. So the IMO gives us mariners all sorts of regulations to follow. So the IMO comes up with the accuracy should not be less than 2 degrees for bearing and 1.5% of the maximum scale for range. So those are the measurements I guess this is where I am a little bit, I'm not sure. If you are not required to have a radar on board and you just have one because you want one, does your radar have to meet IMO standards? I'm not sure. So depending on what type of vessel you are on and if you're required to have that radar on board or not, you might have different standards. I think that all of the manufacturers out there uphold the IMO standards anyways, because they wouldn't want to sell one that doesn't, but maybe you get like a real cheap one or something. I don't know. I'm just saying. Okay. Anyways, okay. This is going to be one of our last ones here. The antenna rotation rate. So we had a lot of rates and frequencies and speeds here, right? This is another one. So the slower the antenna moves, the more time, and this is all like microseconds, whatever, that it has to get a return echo. But the faster it goes, the more targets or echoes that are going out, so the more likelihood that one might get detected. So there's kind of this balance, like of everything that I've said, of finding, slower or faster repetition rate. Now, what did I say last week? Does anyone remember what my repetition rate was? I read it. Let's see if I can find it real quick. Nope. Nope. Okay, here it goes. The antenna is rotating 15 revolutions per minute. So 15 revolutions per minute. Okay. Having a pulse repetition rate of 800 pulses per second would produce 9 pulses per degree. So that kind of gives you an idea of how fast things are going. Have you guys seen the radars moving around on other vessels?
Yeah, so now that makes sense to me, because that's like, it's 4 seconds for it to go around one time if it's 15 in a minute. Yeah, so like.
And that's what you'll see on the radar screen, is that you'll see a glowing line going kind of at that rate.
Yeah.
You'll see it moving.
You're saying that there are a buttload of pulses, though, going on per degree that it's moving.
Yes, that was a pulse frequency of 800 per second. Yeah, that's a lot. So that's why we're talking like that waiting frequency, right? In between a pulse and then the listening is like millionths of a second. It's measured in like, I don't even know how small of a time that is.
That's like 3,200 pulses for one turn in 4 seconds.
Yes. Okay. Okay, so this, oops, sorry. Our next little slide here is kind of, I don't know. I don't think it could quite be in this PowerPoint, but I'm going to talk about it anyways. There are two kind of, I don't know, ways to set up your radar. So the first one I'm talking about here is an unstabilized head-up relative motion. So this means that I have no inputs coming into my radar, that whatever my radar is projecting out is what's coming back. I have no other inputs, no compass, no anything else to kind of like give me an idea of what I'm looking at. So the advantage of this is that if I have a blip on the screen, so we are essentially, if I don't have a compass or anything, I'm head up. So wherever my boat is pointing, even if I'm pointed, you know, east, west, south, wherever, that is going to be at the top of my radar scope. So my radar scope will look like what it looks like when I look out the window. So if I see a blip on the radar off the starboard bow, I'm going to look off the starboard bow and see some sort of target or some sort of something out there. So it matches, and it's easy to detect something on the radar and then identify it as we look out the window. The disadvantage is if you, it's just taking in information, right? So it's not doing this averaging. As we change course or we turn a little bit, those targets you know, target averaging, if you will, can kind of smear, right? Or move the targets when they're actually not moving. It's us that's moving. So it doesn't have this stabilized feature. It's unstabilized. Also, the bearings that we get to all these targets are relative bearings. Have you guys talked about the difference between true and relative when we're talking about bearings? Okay, let's see. Let's talk about that because that is very important. Stand by. Let me bring it up. Okay, so true bearings, when we're talking about true, and everything we put on the chart or take off the chart is always in true, instead of compass or gyro or magnetic or all these other things we can use. True is always measured from true north, right? And our true north is our geometrically, right? It's not actually the North Pole or anything. It's just geometrically where all of the, you know, longitudes meet. That's our north. That's our true north. And everything is measured from that. So when we just look at a compass rose, we have north, and then we go clockwise, and it gets to 359, and then we have 0 again. So everything's measured in relation. Our kind of our datum or our base point is that true north. Now, when we look at relative bearings, we change that reference point or that datum, if you will, to our heading. So a lot of times people will say, you know, something's at 3 o'clock or 2 o'clock or 11 o'clock, kind of use that time, if you will, for bearings around a boat. But I guess the technical term here is going to be relative bearings. So let's look at numbers here. So we have a lighthouse here, and it is on the beam of this boat. So it is 90 degrees right on the starboard beam of the boat. So its relative bearing would be 90 degrees right on the starboard beam. Well, if my actual heading is 045 and I want to plot a bearing to this, I can't say, oh, it's 90 degrees off my beam. I need to get the true bearing. So you have your ship's heading plus your relative bearing to get the true bearing of 135. This one's kind of the same thing, except for we're a little bit further, if you will. Your heading is always measured from north, right? When we say what our heading is. So does this give us numbers here? No. Our heading maybe 135-ish. And then our relative bearing is going to be a little bit abaft the starboard beam. So maybe 100, 110 degrees relative that we have to add our heading and the relative bearing to get what the true bearing from north is. These are some more examples if you want to do some math. My little formula for it is R plus S equals T. Your relative bearing plus your ship's heading equals your true bearing. Okay, I don't think I have to go too much into this. That was a tangent. But when we're looking at, when you're trying to identify something that you see on the radar screen, and then you want to go look out the window to make sure it's a ship or it's a buoy or it's a floating crab pot or whatever it is, you want to make sure that you're looking at the right side or looking in the general correct area. So let's go back to this radar. Oops, here we go. Okay, so when you have a heads up display, right, when on your radar scope, if always at the top of your radar scope is where your bow is pointing, then everything around you is relative on that radar scope. Is that kind of making sense? Okay, so I guess a disadvantage is when you get, you know, use your EBL to get a bearing, that bearing is going to be in relative. So then you have to convert it to true to plot it, whether it be plotted on here or plotted on the chart or wherever. The other disadvantage is that it doesn't match up with your charts. So your charts are always north up, right? Any chart that you work with, north is always pointed up, east is always to the right, south is always at the bottom, west is always to the left. So if you're trying to match up, you know, making an approach to a piece of land, a harbor, or wherever, trying to figure out where you are, and the land matches what you're seeing, but the little picture on your radar doesn't match the picture that you're looking at on your chart, it can be very confusing. So you just have to kind of be aware of it. Now, operationally, some river pilots, or like Mississippi River, that kind of thing, maybe the Columbia River, they might use a head-up display, so that whatever way they're going, upbound, northbound, it makes more sense. But even that, I have not heard of many river pilots using a head-up display. It's not very common, I'm gonna say. Maybe more common in the recreational world, I'm not sure. I'd love to hear if anyone has used, I know most of you guys haven't used a radar, but anyways, head-up display is typically not used. What is used is a stabilized north-up display. So we always have north at the top of our scope, and we have to have an input. So we are kind of relying on this gyro or compass input that we put into the compass. So it's stabilized with a kind of reference point that we can move around, that it knows where north is, because like on a compass, we move around the compass doesn't move around, right? There's the lubber line, and the lubber line is moving around, the lubber line is stuck with the ship, and we are moving around the compass. So same kind of concept here. So great things, our EBLs and our EBLs are all going to be in true, and we're going to match up with our charts, so it'll be easy to see. The only disadvantage is it doesn't match with what you're looking out the window. So if you are headed south and you see a blip on the screen on the right-hand side of the screen, when you look out that window, it's going to be to the left because you are headed south. So you're pointed south. When it's on the blip on the screen, it's going to be on your left. I hope that makes sense. Okay, so that's kind of the disadvantage. And so that's why you really want to correctly identify what you're looking at on the scope and what you're looking at outside the window. So, and I'm pretty sure we're going to go over this again. Yep.
And you would say that you typically have it stabilized north up, relative motion?
Yes, that is most likely how you're going to see your radars.
It's funny. So like I use an iPad for deliveries and stuff, and almost all of the software out there now, the charting, gives you the option to do either. And I would say I just default to north up all the time. Yeah.
Yeah. So. Yeah. I'd love to hear somebody's, real life, how they used head up, but maybe I've learned on north up for my entire career. So looking at head up seems very confusing to me. But if you've learned on head up and that's how you've operated, maybe that makes sense. I'd love to hear about it. But in my experience, north up is how we use all of the radars I've ever worked with. Okay. Quick safety precautions. These radars, emit electromagnetic fields that are very strong. So you do not want to be hanging out up there. So if you have to go paint the mast or do something, you typically put it on standby, so it's not transmitting these pulses, so it stops moving. The antenna stops moving. So when it's safe to get closer to the radar antenna is when it is not moving. It can cause sparks for volatile combustibles. It can produce harmful biological effects in humans. Again, you do not want to be close to these radars. They are very powerful. So keep that in mind. Okay. Okay, real quick here. Again, this is if we were going to be looking at our radar, but we are not. But there is a 7-step tune-up method. So, so we're just going to go over it briefly, but I know you guys aren't going to be doing this. Has anyone been able to use a friend's radar or anything? Seen a radar in use? No? Okay. Okay, anyways, first step is always turn the brilliance all the way up. So I have done this. So many people have done this, where for some reason that radar just won't turn on and you're getting ready to depart and you can't, I'm doing my pre-departure bridge checklist and I can't get the radar to turn on, and it's like calling the engine room, calling the electrician, like what the heck, why can't I get my radars working, when it was just dimmed because we made arrival at nighttime, and it's so bright now that I can't see anything on the screen. So first step is to always turn that brilliance all the way up so you can see it. I've done this a million times. So your brilliance is just like on your phone, you're turning your brilliance up or down, right? At nighttime, we turn everything down so we can keep our night vision. Daytime, we need everything bright, so you turn it up, just like, the lights in your car, kind of. Then you want to turn all of your suppressions down. Your suppressions are your C clutter, your rain clutter, all of those things all the way down. So we're starting no suppressions, right? And then we'd want to turn our gain up. So we turn our gain up to when we get to that snow, if you will, that speckles. Why can't I think of another word of it? I guess snow. It's like the more gain you have, the more returns you're going to get. So if you have your gain all the way turned up, it's just going to be a solid screen. So if you're in open ocean and you're turning your radar on for the first time, you're not going to see anything because there's nothing out there. But you want to turn it down, or you want to turn it all the way up and then turn it down to where you get these, I call it snow, just little little returns here and there, but not like too cluttered where you're like, I don't know what these are. So just this, I don't know, little speckles. I'm totally not describing this right. Okay. Then you want to tune it, and typically you're going to be on auto tune. When you're using a simulator, there's like a tuning bar. There's 2 little bars that go like this. When you move them, you just want to make them meet in the middle and then you're tuned. But typically you're on auto tune, so you don't really do anything like that. So you turn your gain up till you get all of this clutter, auto tune it. Clutter might change, might not. And then you turn it down until you get those little, just a few speckles here and there. Not really maintaining speckles, just popping up and going away, popping up and going away, a little snow. I keep saying that. Then you want to adjust the brilliance accordingly, daytime, nighttime, twilight, whatever it is. And then you can apply your sea clutter or rain clutter depending on what you need to. And, adjusting your brilliance and your suppressions along the way as you need to. Then we're going to talk about our first triangle. How you guys doing? All right. Let's take another quick little break here. I'm going to get a little snack. When we come back, I'm going to talk about radar plotting sheets and kind of introducing ourselves to what we're working on here. So if you have them, bring them out just so you can look at them. If you want to plot along, you can, but yeah. I'll come back in about 10 minutes, 7:45. How are the Dodgers? 2-1?
It's 2-1. We're up. It is top of the seventh, 2 outs. Yeah, we're ahead. This could be it.
This could be it. That's exciting.
That'd be kind of cool. I heard on NPR they said that the Lakers winning the championship and the Dodgers hasn't occurred since like 1980 something.
Wow.
Yeah, that'd be kind of cool. And it's funny. I'm not a native Californian, but I felt like I was my whole life before I moved here. So now I just embrace everything Californian, like, you know, even the Angels.
I like it. All right. Let's look at PowerPoint again. So has anyone seen or used, I guess you guys have seen it, hopefully you have it, a radar plotting sheet? Has anyone used one before? Have you guys have though used charts, right? Taken a basic nav class? Okay, so you familiar with nav tools? Okay. Okay, so we're gonna be using our nav tools. So this is our radar transfer plotting sheet. So let's dive into it. We have our concentric circles, also sometimes called the radar rings, because you can put these rings over your radar screen as well. But they are, when they're on the radar screen, it's an easy, quick distance. Same on the plotting sheet, kind of a quick distance of how to tell where you are. Now, I'm not saying specifically what distance, because over here, just kidding, yep. Over here, we have our distance scales. So over on the left-hand side, it says distance scales, and we have our 6, our 12, our 3, and our 24. So we can make this scope total of 3 miles up to a total of 24 miles. So we are going to be using this scale, and we always want to make sure whatever scale we've set it to, we keep it that way, right? We don't want to flip-flop back and forth. Okay, I'm going to go back here. We have our degrees, right? 0, due north, and then we have the degrees, just kind of like a blown up compass rose. So it makes it easy for us to measure those bearings. When we're measuring our courses and bearings, and we use this circle, essentially, or this compass rose kind of, it always starts from the middle, right? So if you had a line, say like right here to right here, and you wanted to measure it, it's not where that line hits the outside. You have to transfer or move parallel that line to the center to measure the angle of it, or the bearing or course or whatever kind of, you know, the angle of that line. So just keep that in mind. It is incredibly useful to have all of these bearings on the outside, but we want to keep in mind when we're measuring our bearings, it always starts from the center when we're getting that number. Okay. We have our distance scale on the side. Again, we could use them. I like to, whatever one I decide I'm using, to cross out the other ones so I don't get confused and easily go to another one. So that's good. On the right-hand side, on mine it says speed scale. Do you guys have one that says speed scale, right? That speed scale is only, let's see, 12 knots. We're not going to use that speed scale or the logarithmic scale at the bottom. We're going to use 60 D Street. Have you guys used 60 D Street before? Okay. So speed, distance, time in an equation. You could use it in an equation. You could use it in the magic circle. Does anybody here use the magic circle? Okay. Who uses the equation? Okay. So that's how we're going to be converting our speed to a distance. And then we use the distance scale to put in, to make our vector have those two components, a direction and a length. Now, let's see. Maybe I'll get through this a little bit. Well, okay. That being said, using 60 D Street, a knot is a nautical mile per hour, right? Nautical miles per hour equals a knot. So if you were going 5 knots, you would go 5 nautical miles in an hour. So if we set the whole triangle to a 1 hour scale, then we don't have to really use 60 D Street. Our 5 knots is equal to 5 nautical miles. Everything's on an hour, and the math is super easy. So that's what we're going to try to do to make it easy for us. But as you'll see, sometimes we make it challenging. Okay. So this one's real. Let me new share. Okay. Can you guys see my paper, right? Here we go. So when we are using our radar transfer sheet, basically, we are transferring what we see or what we find of something of concern on the radar screen. And then we're transferring it to this paper plot so we can determine if there's risk of collision, essentially. So maybe our radar screen has some land. Maybe we got a little buoy, which, you know, doesn't look like that on the chart. It just looks like a blob. Then we got some blobs. Let's talk about this blob right here. So this is what it looks like on the radar. And when we transfer it, I want to know if this target up here is going to be of concern. So I go to the radar screen and I get that range and bearing using the EBL and VRM, right? The variable range marker, and we put that right to the very, very blip right there. And then we get the EBL that goes directly through it. So we get our EBL and our range, and I'll say, okay, right there is where it was at a certain time. So I go on the radar, use my EBL and VRM, and I say, okay, at, what is it right now? 1955, it was right there. Then I want to wait. So I have a picture of what happened in 1955. I put a little dot on the screen. And then I wait. And we're also going to learn another quick way to do 60 D Street is to do things on the 6 minutes. Does anyone know why we do it on a 6 minute? 6 minutes. So 6 minutes is 1/10 of an hour, right? So that would be 0.1, if you will. So if you times 0.1 by another number, all you have to do is move the decimal over 1, and it quickly translates to speed and time. So it's a quick way of doing numbers, the 60D street. 6 minutes is used a lot in the commercial industry. If we were making arrival or making departure and it was at 6:55, 1955, I would write it as 1954 for the 6 minute. I want everything as a multiple of 6. So when I do my ETAs and my, fuel consumption and all of those other calculations that the office wants and stuff, it's easy and you're not working with long decimals. You can say I traveled for, 86.2 hours, and it's an easy conversion. Anyways, you'll see we use a lot of 6 minutes a lot as a tangent. Okay, so 6 minutes later, I am going to see where that blip is again. So I'm going to see range and bear or VRM EBL on my radar scope. Let's say it's right there. 6 minutes later. So that's what happened at 20:01. That's where it was. I got my EBL right in the middle of it and my VRM to say right there. So I have what it has done in 6 minutes. Now, if I continue my course and speed, this ship continues its course and speed, then this vector that we're creating will continue on and on. So if I connect these two dots, this becomes relative motion line. So if I am here, I don't know, maybe I'm over here. Doesn't really matter. Wherever you're pointed, if I continue my course and speed and it continues its course and speed, 6 minutes later, it'll be right here. 6 minutes after that, it'll be right here. 6 minutes after that, it'll be right here. Continue and continue. It will continue along that line. So in this case, I would say risk of collision does not exist, right? It's relative bearing, even if it's pointed directly at me, relatively, it's going to be following this relative motion line. So we want to know what this relative motion line is so we can determine if there's risk of collision. Are you guys following me so far? Any questions? Okay. Now let's look at got a million of these. Okay. Let's put us, we're going that way. But again, we're north up, so we always have north up. If we use our radar, range and bearing, let's plot, we got something kind of brought off to the starboard side. Let's call it 0 to 5 at 10 miles. So I am going to use my 12-mile scale. So I'm going to cross those out, not use those. This is the one I'm using. Okay, I got to cross it out. Let's make it 11 miles. It's 11 miles away. I'm going to use my dividers to plot 11 miles away. So I measure my 11 miles, and its bearing was 025. So I'm going to mark right here. That's where it was at, I don't know, 12 o'clock. Okay, now I'm going to wait 6 minutes or 12 minutes, 18 minutes, however long. Typically we use 6, and see where it is later. 6 minutes later, I get my range and bearing. So if we were in class and we were doing this together, you guys would be seeing that blip on the screen moving, noting it at one time, waiting 6 minutes, which you can do a lot in 6 minutes, right? 6 minutes is a long time. And then plotting another little blip in 6 minutes later, range and bearing. What was it bearing? Let's say it was bearing 023. So we'll do 023 at 13 or 9 miles. We'll do 9.5. How about that? 9.5. Here's our 9.5. Blip. There's a little dot. So now I can connect what happened at 12:06 and what happened at 12 to get a relative motion line. So if I connect these two, I am going to get a relative motion line. Now, this case, I am coming within how many miles? Quick guess.
4.
2. So here on our scale, we have bold, 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 not so bold, 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 right? So we have 2, 4, 6, 8, 10, 12. Those are our range rings or our circles. So I can see I am right at the 2 miles. Now I also see that this vessel will be crossing ahead of me, not behind me. I don't know as of right now what that vessel's true course is, like who has the right of way. I'm trying to decide if I want to do that right now with everyone. Yeah, let's do it. Okay. So, okay. Yeah, let's dive into this. We got time. We got like 2 hours here. So the first little blip, we're going to label these with letters. And this will help us determine what kind of lines we are going to be looking at. So our first little blip, we're going to label R. 6 minutes later, wherever that vessel or that target is again, we're going to label it M. Now, R to M, what do you think that stands for? Relative motion, right? Our relative motion line. If we connect R to M, we are creating our relative motion line. Motion line. We are creating that relative motion line. So then I need to transfer, and this is where, so what I'm going to do next is make a little triangle here. I don't need to go back to PowerPoint. I'm going to make a little triangle here to determine what their true motion is, or their true course and speed. So how do I figure that out? Is there any other piece of information that I can use to help me? What do you think? What do you think the other piece of information is?
Well, you have distance and you have time. You got to be able to figure out speed.
We can figure out, so if I get this distance right here in 6 minutes, my relative motion is 1.5. Everyone see that? 1.5. So my relative motion speed would be 15 knots. That's relative motion. So what is happening true motion? So the slower the relative motion is, the slower, this is going to be. I guess that makes sense. Yeah. Anyways, the other piece of information we have that we haven't really plotted is our own information. What is my course and speed? So we're saying if this vessel is staying on its course and speed and I'm staying on my course and speed, this is what the relative motion is going to be. But I want to plot, forming a triangle here, what my course and speed is to help me figure out the rest, essentially. So how I do that is I transfer my heading line, and I didn't give us a speed. Let's make our speed, so our course was 330. Our speed is, let's go 10 knots. As you can see, I'm making this up. Okay, so I want to transfer my line and create this vector. So I want to create this vector. How I create this vector, I make a line in the direction of 330, and I set the distance. I'm putting this in an hour. So I set the I'm not putting this in the hour. I know I said that before, but I'm changing my mind. I'm putting this in 6 minutes because this was at 12 and this was at 12:06. So we have that 0.1. So if this is 10 knots, I'm going to move my decimal 1 over, and I'm going to travel 1 nautical mile in 6 minutes at 10 knots. So you can do the 60D street to check my math there, but we're going 1 nautical mile in 6 minutes. Okay, so I want to transfer my 333 line over to the R. Or R is our start point, and that's where we're going to move it over to the R. Look, I didn't do it right. So I have a line that is in the direction of 330, right? Going this way, that line is 330 because we measured it from the center. Then I want to put my speed, which I put in as my distance, 1 nautical mile. This is a really small triangle for an example. I wish I did a different one, but so now we have another dot. So this is my vector, and we are going to label that E. So E to R is the own ship. That's my own thing, what I'm doing. I am going 10 knots, so 1 nautical mile in 6 minutes, in the direction of 330. Now I can connect 2 more dots. E to M is them. And there's going to be little rules here. You don't have to memorize any of this. This is just an intro, so next week isn't as painful. So now I know what that vessel is doing. That's its true motion and true speed. So it is going along there, but its relative motion is going to be cruising this way. Does that make sense? Its true course is whatever that is, but its relative motion is going to be headed in front of me. So if I look at this, 2 power-driven vessels, who is give way, little speedboat or container ship, and who is stand on? Okay, who votes that okay, I'm a little speedboat here. Who votes that I am give way? Who votes that I am stand on? All right, we're gonna get good at this, right? Okay, does anyone remember the rule? 2 power votes crossing. Who has the right of way?
Let me just preface by saying prudence dictates that a little speedboat gets out of the way of a container ship.
That's very true. Imagine this being another container ship. I don't have any other toys. But I like this one because it's boat shaped. It matches my little drawings of boats. I'm not an artist. Okay. The vessel to starboard has the right of way. So if we go back to what is this vessel's lights? We have green on the starboard side, red on the port side, right? We have green on the starboard side, red on the port side when we're looking at our nav lights. So as this vessel, I am seeing a red. Stop, red. I need to give way. This vessel is seeing a green. Go right ahead. Keep it on moving. So this vessel has the right of way, or the stand on, if you will. This vessel gets to maintain course and speed. This vessel, which is me, because I'm the center of the scope here, is the burdened vessel, or the give way, whatever. How do you guys learn it? Help me put it in ways that you guys will understand.
Give way vessel.
Give way stand on? Okay. So I am the giveaway vessel because I see this red. So I know that if I don't do anything, this guy is going to pass 2 miles ahead of me. Maybe I'm cool with that. Maybe I'm not. I don't know. Up to you. But if we're looking out the window, we just see him crossing over here. And then all of a sudden, he's going to get closer and closer and closer to us. So we want to know by how much. That's why we want to know what the relative motion line is versus its true motion line. So now, and that's a lot of clutter on the page, right? I just showed you a lot of little work here. I'm going to show you back to that video. Where's my video? There it is. Okay. Let's hope there's not any voice on this video and I can just talk over it. Play. Okay. So as you can see here, wait, let me go back to this one. Here are our lines. These are our vectors. Now, these are plotted with ARPA. So ARPA is the way that does what we are going to learn to do by paper automatically. So this is just visualizing what we're actually looking at. So I have set in this case here, these vectors are on true vectors at 16 minutes. So that's saying if I maintain my course and speed and all of these vessels maintain their course and speed, in 16.7 minutes, this vessel will be right here. I will be at the end of my line. This vessel will be at the end of theirs, et cetera, et cetera. So it's giving this projection of what's going to happen in however long I set my vector to. This case, it's 16 minutes. So these are true vectors. Did I say relative at the beginning? This is what true vectors are. So, and I can also see that because the trails are on. So the trails also help giving us that true, what that vessel is doing true. Now I'm going to push play again. And I'm going to toggle back here between relative and true. So let's pause here on relative. So relatively speaking, these two vessels are going to pass behind me. This is the center of the screen. This is me. These two vessels are going to pass behind me. This vessel is, or this target, excuse me, is not moving. It is just paralleling what I am doing at my same speed. This vessel is not moving. This vessel is not moving. This vessel is, but it's still going to pass behind me. So let's go back, look at it true. So when I look at these, they don't have any of those trails, right? They don't have any, I don't know if they're moving or not, but I'm going to say they're not moving. They don't have any true target or true vector, right? So these guys here are not moving, and here's my vector. So if I'm going to end up here in 16 minutes, I could kind of see that this person is probably going to pass astern of me if they're going to be there in 16 minutes. But it takes a while to like, you know, process what you're looking at. But I'm just kind of giving you an example ahead of time. So let's play this. I think I toggled back and forth a little bit. So here's our relative. Again, I go back. This guy is crossing in front of me, and I could see that. Relatively, I might want to know what my bow crossing distance is. How close is he going to get to my bow? I might want to measure that. Okay, see, we're moving our vectors to 30 minutes. So you get all sorts of big lines the bigger the vectors are. But sometimes you want to see them cross you so you know if they're passing ahead of you or behind you. Okay, I bring it down. I don't know. I guess I'm just toggling here between true and relative. Do you guys have any questions about what I'm talking about here? Is this visualizing kind of what I did on the paper?
That actually made the stuff on the paper make sense.
Okay, good. That was my hope. Okay, so here we scaled down. Now we're only looking at 6 miles. So that is a great tip. If you start plotting all of these things and there's lines going all over the page, and what are we looking at? We're going to look like, we had one where there was lines all like this, and you're like, oh my God, this is so scary. I don't know what's going on. To make it simpler, scale down. Go from 12 miles to 6, or go from 6 to 3, because then you see, what do I have to deal with first, right? What's going to happen in the next 6 miles here? And then I can decide what's going to happen after that. But I don't need to add more stress to my situation, that if I'm overwhelmed, it's good to know what's happening 12 miles ahead of you. That way you could plan for it. But if you're overwhelmed and it's too much to take in, just narrow your scope and focus on what's happening next, which essentially is at a smaller scale. So here, I think I'll toggle back and forth. We have our relative motion. Again, these guys aren't actually moving. So their relative motion is opposite of my true motion, right? This is my true motion. Their relative motion is exactly parallel and paralleling my speed. This guy is moving, so his relative motion, it will be a little bit different. Let's see if I go back to true. I don't. There we go. There is our true. Anyways, I'll probably go back to this video a lot to try to help us explain what we are looking at sometimes. But I don't know. Let's go back to my paper. So this ends up being very sloppy right here. But next week, we are going to go step by step how to do this and do lots and lots of examples. So hopefully you guys can do that along with me. Have your plotting gear. I prefer the triangles. That's what you'll see me using a lot. But I'd actually like to use whatever you guys are using. What are you guys using?
I have like a rolling ruler thing and
The roll plot.
yeah.
Okay. Who else has a roll plot? Okay, who has parallels? Wait, was that most hands on the roll plot, right?
Yes.
Yeah? Okay, I'll use the roll plot. And then you'll want your dividers. I actually like on the radar plotting sheet doing the compass. That's one pointy end, one pencil end. That way, sometimes it's easier than just kind of trying to like scratch it and remember where you put it. That I tend to use the compass, one pointy, one pencil, rather than the dividers. But either one will work. And that's all I got. Any questions? Okay. Again, on that Canvas for the assignments, this week's homework assignment is a like fill in the blank theory questions. So you can go back to the PowerPoints. They're on the Canvas as PDFs, or you can listen to or watch the recorded Zooms again. But I want to say most of the answers will be there. Some of the answers at the end of the homework assignment are going to be a little bit later, but that's fine. You guys will get it as eventually. The answers are also posted on Canvas. So you have the questions and the answers. Use that as a study guide. It's a great review for the theory exam. And for the turning in of the assignment on Canvas, I forget what I put your name or the date or something. But again, click that submit assignment twice until you get the confetti raining down on the screen, and then you get the status of completed. So yeah, that's all I got. Any questions? You guys doing okay with your other classes? Any other maritime questions I could help with? What other maritime classes are you taking right now?
I've got maritime industry and maritime environment.
Industry and environment. Okay.
Environment and boat handling.
Boat handling. Do you guys do chart plotting in there? Boat handling, or is it just boat handling?
We've done about one exercise so far, but the rest has been just boat handling.
Okay, cool. Is
I
there
had
radar on any
navigation
of
last
those?
month.
On none of the boats we're using have a radar on them. No.
Which boats are you guys using?
We're using the Boston Whalers at the boathouse.
Which one? Sorry.
The Boston Whalers.
Oh, just the Boston Whalers. Okay. That's cool.
So,
That's a fun
yep.
class though.
Yeah.
Yeah, so Louise, you asked about the recordings. Let me show you on Canvas. Okay, I'm gonna share screen here. Okay, so if you go to Canvas and you click on Breeze tutorial videos, you get brought to a thing, and then you go open a new tab, and you get a YouTube channel. Go to, instead of going through all of these videos, because I'm teaching another class too, it might get confusing, go to the playlists and click on radar. When you click on radar, I just have one right now from week 1 of this class a week ago. So the 2-hour video is posted here. So if you can't find it, please let me know. It is on private, but all of the emails that you guys sent me last week have access to it. So if you can't get access to it, please let me know and I'll get you access to it. I am new to YouTube, so yeah, I guess I'm not an expert. I'm not great at it, but yeah, we can make it work, right? We can do it. So when we start doing our homeworks where we have lots of paper plots and questions, I will be doing those in a homework tutorial. That's why it's Breeze tutorial videos, and posting them here as well. So remember to go to the radar playlist. So we have, yeah, I have Coastal Nav 1, Coastal Nav 2, Celestial, but go to the radar one and you'll see all the radar things. So yeah, that's what I got. And it does take Zoom a while to like download this. Like I literally start downloading it at the end of this class, but it might take me a day or two to actually post. So that being said, hopefully it'll be done by the weekend though. Well, yeah. All right. That's all I got for you guys. Have a good week.
Take care. Stay safe, everybody.
Bye.